So in this session, we will be designing and modeling the piles for the high-rise building, and this is session 8, in which we will be calculating the pile capacity. So how do you calculate the pile capacity, or where you will get the piles capacity? And then we'll move towards the how do you calculate the number of piles required for the foundation, and then we'll move towards the design of modeling of piles and design, and this is the modeling and design of pile, right? And then again we will be the design of the raft in the surface per the CA 1840, right? So for the design of piles, we will take the same 12-story high-rise building, and this time we will consider the allowable bearing capacity is 1.2 TSF, which is equal to 2.65 instead of 2 TSF, which we have taken in the previous session for the design of the raft, right? So the demand is the same because the structure is same, which is this one, 12-story building, and the demand is coming from the superstructure is 3.9 KSF, and this time the allowable bearing capacity is less than the demand, right? This means that if you provide the raft, which we have provided in the previous session, will not work for this building, right? So I've already explained some of the options that you have to increase the area of the raft, or go for the piles, or decrease the number of the story. But there is no option to decrease the number of story or increase the area, and the client still wants to build a 12-story building, then you must go for the piles, right? So the total demand is 3.9 and the capacity is 2.65. The total service load of the 12-story building was 124,909 kips, and the area of the raft were 32,000 square feet, right? So how much load the raft can resist? So let us calculate. So the total load that raft can resist is that you have to multiply the area of the raft into the allowable bearing capacity of the raft of the soil. Then you will get this much force, which is equal to 84,676 kips. So this much force the raft can resist if you provide a raft area equal to 32,000 kip square feet. So this is the total load, and this is the capacity of the pile in kips. So you have to resist the remaining load with the piles. So how much load the piles will resist? So you can calculate the loads to be resisted by the piles, and you have to subtract the capacity of the pile from the total service load, and you will get this 40,233 kips. So this much force should be resisted by the piles in order to safely design this 12-story building foundation, right? So this was the whole story about the calculation for the forces, the capacity of the raft, and the load required to be resisted by the piles. The next step is to calculate the number of piles. So how do you calculate the number of piles? Normally, the pile capacities and these graphs are already, you will get these graphs and capacities from the geotech report. You will ask that consultant to draw these graphs and calculate the piles capacity for you. So it will make your job very easy. Otherwise, you can also calculate it from the SPT number. There are different formulas in the Bowles book. You can search it and you can also find it. But normally, what we are doing in our consultancy, we get this already built graphs from the geotech report, and we calculate the pile capacities and we design the piles, right? So we have to select the pile capacity, dia, and length of the pile from the geotech report, and this is the shape. This is one of our actual project, and this is the Excel sheet for it. That they have given us this Excel sheet that there's a pile dia, which is in inches 12 inches, and this is the length is 20 feet, 40 feet, 60 and 80, and these are the capacity in kips. And this is the pile 18 inches dia, and its corresponding length and capacity is same for the 24 and 30 inches. Normally these uh, board piles are used in practical, but you can also design your own pile dia. For example, if you are want to work with the 15 inches or 21 inches dia pile, but then you have to make your own bolt or the bolt size for the boring of the pile, and it will be much costly. So you have to work with the available uh, boring molds, so it will be very easy for the construction point of view. So this is how you will decide the pile capacity, and these in this graph you can see on the y-axis there is the pile capacity in kips, and on the x-axis there is the length of the you can see the depth of the pile in feet, and these are the different graphs. So the blue one is the for the 12-inch dia pile, and its corresponding capacities to 20 feet, 40 feet, 16, 80, and similar for the 18 inches and 24 inches and 30 inches. So you have to select the pile dia and length and the capacity from these graphs, right? So in our case, you can select any dia any length as per your design and per your requirement. So we will select 30 inches dia having 40 feet length. So the capacity of this you can see, you can also take it from the table as well, from the graph. So let us use the graph. Say the 30 inches is the yellow one, and the capacity for the 40 feet is 790 kips. So this is the capacity of one pile, right? So the next step is to calculate the number of piles. So the capacity of the one pile is 790 kips. So if you divide the total loads to be resisted by the piles by the capacity of one pile, you will get the total number of piles required to resist this load. So we need 50 piles having 30 inches dia and 40 feet length. So these piles has to be provided under the raft, and you have to design it to resist this superstructure load, right? So this is the first case. If you do not want to go with the combination of piles and raft, if you want to go for the pile capes, then you have to resist all of this load with the piles. Then you have to divide this total load by the capacity of one pile. So let us do this. For example, if you do not want to use the raft for the in the design, you just want to resist all the load by the piles, so then you have to provide 158 piles to resist all of the load. We're having no raft, only with pile capes. So then in this way you will play with the capacity and the dia. So this is the maximum dia, so you can go for the 80 feet. So if you use 80 feet length dia, length with 30 inches dia, and the capacity of it is 1890, so you will need 66 piles, right? So sometimes you will increase the length or decrease the length. For example, if the area is very small and it requires 158 piles, and you cannot adjust that in the area available for the plot, so then you have to go for the more length. So in this way you can play with the length and the number of piles and diameter of these, right? So this was the whole procedure. If you go for the design of pile with raft, or would you go for the design of pile without the raft with the pile cape, right? So this was the whole story about the number of pile and pile capacity. The next step is to model it, right? So the important point is the modeling of the piles accurately, that you have to distribute the piles equally across the raft, right? So let us go to the model, and let us go to the, so this is the raft, and you have to place the piles very carefully, and you have to distribute it very equally to distribute the load coming from the superstructure into the raft, and the raft will take some load, and when its capacity is reached, it will transfer its loads to the piles, right? So the first step is to draw the piles in the ETAB model, and for this you have to go for the modify story command, and then you have to insert another story, like just like I have inserted the pile tip, which has the story length is equal to minus 40. It means it has 40 feet length from the base of the raft, and then you have to click on OK. You can also insert like this. For example, if I insert, you have to insert add story, and you have to insert this keep the height story, and you have to insert the this one. This is the elevation, right? So you have to insert, for example, if you want to add in 80 feet, you have to insert minus 80 and click on OK. So the on minus 80, there will be another story added, right? So in this way, how we will add the story for the piles. Right, so the next step is to define it. So you have to go to the section properties section, which I have already defined. This is pile. So let us go to the add new property and click on the circular and click this is pile 30 inches die. Select 3000 and insert its die to 30, right? Click on OK and click on. Now you have to go to the draw quick command of the columns and draw this pile which is 30 inches in diameter. So you have to distribute these piles accurately across this raft, right? So this is the top. Now let us go to the basement. This is the raft, and you have to draw the piles, and you have to distribute these piles, and you have to do this in you can also do it in the AutoCAD, but at a specific distance, and it will take a lot of time. I am doing this just for the understanding purpose that we have to distribute it equally across the raft, right? So after that, for example, let me show you in the model which I have done to save the time, because remember that in the design of the model in ETAB, it will take a lot of time, right? So after the division into segments and you assign springs, so the file will become very heavy. What I have analyzed this structure, it took 2 hours to analyze this model, right? So try to keep the segments as much larger if you can. For example, if the length of the pile is 40, so if you divide it into 1 feet, so it will be equal, because if you divide that segment into 6 inches or 5 inches, it will become a lot of piles segments, and you have to assign the springs into the all segments, and it will take maybe 3 hours and 4 hours to analyze this model, right? So this is the model which I have distributed these 50 piles equally, and after doing this, then you have to go to the 3D, and you have to display only these limits, which is the pile tip and the basement, and then you have to select the piles, and you have to edit and divide these frames as per your choice. So I will recommend to divide it into 1 feet or 2 feet. So if it is 40, so let us divide it into 2 feet. So we will divide into 20 parts, right? So if you divide into 40 or 60, so it will give you more accurate results, but it will take a lot of time to run the analysis. So in this way, you have to divide these objects into 20 segments. So now these are the you can say 20 piles, and you have to assign springs into it, right? So the next step is to define the lateral and the vertical springs to represent the soil. And these are the some equation which is given in the Bowles book and other, this is Charles book. You can find on the different literature on the research gate, or there are many equations. You can use any of the equation. So I have included in this session this equation that for the clay you can use this equation where the D is the dia of the pile, and K naught is the uh, coefficient of the earth pressure at rest, and this is the density of the soil, and X is the depth of the pile, and tangent this is the angle, and this you can see the K naught, you can calculate it from this equation, right? So for the sine it is taken as one, K naught is 1, because this angle is normally very less for the sand, and for the clay it is normally equal to this equations, which is the angle is normally it's 25, or maybe in between the 25 or 30, and for the sand it is normally the K naught value is equal to 1, right? So for the practical point of view, the value of K naught will always be equal to 0.5, or the value will in between the 0.5 or 0.45. So I have taken it, this value is 0.5. So the depth, the diameter of the pile in our case is 2.5 feet, and the K naught is 0.5, and the density of the soil is 120, and this is the length, this is the 40, right? And this is the tangent 25, which I have taken this angle of internal fraction, and then you have to calculate the EV. So this is the one method in which you can use and calculate this KV. Another method is the force deformation curve, which is also available in different literatures, and I have also explained that there are different equations you can use to calculate the springs, that it is the force divided by the delta. You can also use this relation to calculate the stiffness of the spring, right? And what does it mean by force? Force means the capacity of the pile, right? For example, if the capacity of the pile in our case is 790, and you have to divide it by the allowable settlement. Delta is the allowable settlement of the pile. So from different researches and different case studies, it was found out, you can also find it in the books, that if a pile penetrates or settle 10 millimeter, it will be considered as a fail, just like we did in the Raft for the 1-inch settlement, right? So if you divide it by 10 mm and you convert it into inches, it comes out to be 2006.6 kip per inch, right? So now this is your choice, which equation you will use in the calculation of the springs. So normally this equation is also used, and you can also this equation, right? And this is the KV. KV means this is the stiffness of the vertical at the tip of the pile. This is the spring constant at the tip of the pile, and to calculate the KH, which is the horizontal, to represent the soil inflection, we have to increase this value 10 times, right? We have to multiply this value. So these value I'm using, these are for the different researches and different values, and it is using practically in Pakistan. So this is how you calculate the spring for the tip, or for the, this is also tip per inch, right? So you have to insert these values in the ETAB. So I have included this, but I will be using this calculations in the ETAB. You can also use this equation, and you can use any other equations in the books and the literature or different case studies. You can use any equation, right? So let us go. So you can also calculate this. This is not equal to the, because I have calculated for the 80, and you have to calculate it by yourself. You can also do that because I am using this force deformation, or you can say P delta relation. I'm using these spring constants. So let us go to the ETAB, and we will go to the define and go to the springs property and point spring, which I have already defined. So let me define new one to explain it. So click on new property and check the, for example, let us call it as a tip spring, right? And you have to insert the translation in Z, and you have to insert the value, which is 2006, which is keep per inch, right? And you have to keep all of these 0. And now you have to click OK. Again, add new property, and you have to write the lateral springs, and this time you have to insert the value is equal to 0.0066. I think this is the value. Yes, and same for the other direction. And now you have to click on OK. Okay. Now select the pile joints. You will select all the pile joints which have you drawn, but I have not drawn all to save the time. So you have selected all of these joints of the pile, and you have to go to the assign join springs, and you have to insert the lateral springs and click on apply. So now this lateral springs has been assigned, which will represent the soil. Right. So at the tip, let me check it. I'm not satisfied with this direction. One spring, lateral spring. So this must be 0. Right. So this translation must be 0, and click on OK. Now again you have to select. You have to very carefully define these springs, like that I have assigned it and now I was not satisfied, so I have rechecked that, so that what happened. So again you have to assign the spring and lateral spring. Now it has only assigned the lateral spring, there is no vertical springs, right? So now you have to assign the vertical springs only at the tip of the piles, right? So assign these, select the tip of the pile and go to the assign joint springs and spring the tip springs, right? So now you can see the direction of the springs in the upward direction, right? So this is how you will model the piles in the ETAB. And again, for the raft, you have to assign the soil properties to it. That is, you have to define the area springs, which I have already explained in previous sessions, that you have to, which is 1.2. So you have to define this subgrade modulus, and you have to click on the compression only, right? So this is linear. Linear means that it will take all of the load, and for the compression only, it will transfer the load into the piles, right? So this is click on OK, and select the raft and go to the assign shell and click on the area springs and like this. So now you have to confirm whether this spring has been assigned or not. So right click on the raft and you can see in the assignment that the spring has been assigned, which is 1.2 TSF, right? So for the initial, the thickness of the raft will not be changed because we used 42-inch raft because it was the requirement, and it will be remains the same, right? So what I have analyzed is the 36-inch, and you can increase this value to 42 because 42 will work, which we have seen in the previous session that 42 was enough and 36 was not enough for the punching check, right? So if you check this model, so this is the same model, and these are the same springs which I have assigned into the piles, and I have run the analysis because this analysis took 2 hours to complete, right? And you will observe and you will see the same results, that it will take hours to complete the analysis due to the inelastic springs and due to the different segments of the piles, right? So the first step is to check the punching check. You can also check in the ETABS, or you can transfer into the save, because both will give you same results. These are the CSI softwares, right? So this was the whole story about the modeling. And what I have included in this lecture, that the UBC97 also give you some direction for the uncast cast in place piles may be assumed to develop a friction resistance equal to 1/6 of the bearing value of the soil material, which is the 16% of the vertical tip stiffness. You can take 16% of that to represent the soil at the lateral. But this is the one condition. You can also use different equations, which I have already explained in the beginning. You can use different equations, different formulas and equations are available for definition of these springs. The next step is to divide these piles into segments and assign the springs to each mode, and then run the analysis, which we have done. And now the next phase is to design the piles. And for the design of the piles, you have to must check for the punching, that the pile do not punch or the column do not punch into the raft or out of the raft. Right. So the next step is to check the punching. You can check it in here, that this is the complete slab, and click on the display punching check. Right, you can see it took some time because it is very heavy, and you can see that the ratio is 1.36 because I have taken the raft thickness is 36 inches. But if I unlock this model and start running the analysis using 42-inch raft, so it will take 2 hours. So, right, so the conclusion is that you must go for the raft thickness 42, which you have previously designed. And now in this model, you have to design for the design of the piles. What will be the reinforcement of the piles, and on what combination you will design the piles. Normally, the piles are designed for the factor load, gravity factor load, because the earthquake have very less effect on the piles because these are embedded in the ground. When the ground shakes, these piles will shake with it. So there is no significant effect of the earthquake, but there is a significant effect of the flexure loads, that is axial load coming from the superstructure. So you will go to the design of this pile. You have to check the combination, and you can see these combos have all combos has been included in the design. Right, so we will design it for the all combo, and you will see that if you design it for the earthquake, it will give you too much reinforcement, which will not be economical, it will be uneconomical. So we will display the design info and click on the apply. Right, so let me show the 3D. Right, so these are the different segments, and you will see that the reinforcement will be very high at the top, and it will be decreasing if you go down, because code allows you, ACA code allows you, if you provide reinforcement to the 1/3 length of the pile, and if you do not provide any reinforcement beyond this length, and if you provide only sort of if you provide only PCC concrete to this 2/3 length, it will work. But for the, you can see the field uncertainty, you must provide the whole length reinforcement, right? So if you see the behavior of the bending moment, so it will end at the 1/3, right? You can see this is the bending moment, and you can see it is very high, and now it is decreasing, and it is almost 1/3 length, and it's become 0 and very negligible. There is 0 bending moment at the bottom, right? So this is how and why the code allows you, if you do not want to provide reinforcement at the after the 1/3 length, or you can minimize or decrease the reinforcement, you can do that. Code allows you to decrease the reinforcement. So first of all, you have to check the pattern or the behavior of the raft and piles, whether this is accurate or not. If the bending moment is not vanishing at the 1/3 or half length, so there is some mistake or there is some error in your model. most of the time it will end at the 1/3 length of the pile. So this is the bending moment. So let us go again to the display design. So this is the design, and you can see it is 1% in here, and it is very large percentage of reinforcement, right? So this is designed for the earthquake 0.99D and earthquake. And if you click on the summary, right? So let me right click on the, there is some issue. Display the percentage. So now you can see that the reinforcement required at the top, it is 2.87, and it is decreasing if you go down, it is 1%. Right? So if you use 2.8%, it will be very, very large reinforcement if you are designing for the earthquake, right? So this session is about to end for the Zoom, and let me end this, and we will again join a new session, and we will again resume from the design of the piles from here.